Okay, we're going to talk about E2 with alkyl halides. We call this, once again, dehydrohalogenation. There's a couple of things that we need to address before we go into the mechanism. First of all, using a large, strong base will favor E2. And once again, the large is important so that we don't get substitution, because there is a battle between SN1 and E2, or E2 and SN2, sorry. And that'll ensure that we don't get substitution products if we want to get our alkene products. Another thing to consider, and I didn't really mention this in the E2 with alcohols, but it's the same, it's true for both, that it's a concerted mechanism. And that means that everything is simultaneous. It's not one step and another step and another step. The entire mechanism happens all in one huge step. I referred to beta and anti-elimination before, and here I'm going to go into it a little bit more depth just to make sure that we understand it. Okay, so if our alkyl halide looks like this, it's secondary, we know the halogen is going to be our leading group, and that the carbon that has the leading group is the alpha carbon. So in this case, we have a beta hydrogen here, or carbon here, and a beta carbon here. I've only labeled one, so we're going to deal with the one that's going to give us the major product, which is this carbon right here. So strong bases, what are strong bases? Well, anything basically stronger than, about as strong as hydroxide and stronger, we consider strong bases. Deprotonated alcohols are about the same base strength as hydroxide is, so we consider them strong bases. So right here, that's what I have, it's a deprotonated alcohol. This is tert-butoxide in this case. And it's one of the largest, or one of the most sterically hindered bases that we can use, and that's what we mean by big. It means that it can't go into there very easily and do substitution. So you notice that this directly off the oxygen is all this huge mess of carbons. So what is it going to do instead? Well, it's more easy for it to remove a hydrogen than it is to get in there and do substitution. So that's what it's going to do way more often, is it's going to remove one of the beta hydrogens. The way I have this drawn is that the bromine is anti to this hydrogen right here. And I've gone into more detail and shown how that works right here. So really, we know that there is stereochemistry going on in a molecule. It's not just planar like this. So I showed a wedge and a dash here. The bromine's coming out at us. The hydrogen's going into the board. This is an I, so we're looking down this carbon to this carbon. So this carbon is going to be in the front. This carbon is going to be in the back. And if you have a model kit, you can actually make this. And what that allows us to do is visualize a Newman projection. And we can actually, and this isn't something that your teacher's going to do usually, is do a mechanism on a Newman projection. I'm just doing this to show you how I visualize it, and maybe it can help you see how it works. But when we say beta or anti-elimination, this is basically where it's coming from. The hydrogens are beta, and the anti means that in order for the p orbitals to line up, which I've showed that in the hyperconjugation video. You can look that up to see how this works in more detail. But the leading group, or the bromine, and the hydrogen that gets removed have to be anti. And that allows the pi orbitals to line up and stabilize the molecule when these two, when this and this leave. And so that's what we see here in the Newman projection. And the substituents, these two methyl groups, are also anti when these two are anti. So when we get the elimination here, our final product better show these two being anti to each other. these two methyl groups. So this methyl group is this one, and this methyl group is this one. And that's what we see as the final product. And we would expect that to be the major product because these are the furthest apart. If we were to rotate this at all so that this hydrogen were here, we would have steric hindrance between this and this methyl group, and that would give us this product as a minor product. And you could show how this is a result of this thing being spun around and giving us the minor product here. And that's basically E2.